Okay, so I'm going to talk about Nickelate superconductors, and I will focus on our dynamical vertex approximation calculation. As you will see in a minute or two, the results are actually much better than we dared to hope for at the beginning. We can then discuss whether it's by chance or not, and what differently to predict, to see whether it was by chance or not. Before I start, I'd like to thank my co-workers, and in particular these four young guys here, Liang Xi, Motoharu Kitatani, Paul Worm, and Simone Di Cataldo, who did all of the actual calculations I'm going to present today. Okay, but let's jump right into nickelates. 4 years ago, Denver Lee, Harold Wang, and co-workers discovered a new class of superconductors, nickelates, and that is the figure from their original paper. So they have 20% strontium doping of neodymium nickelate, and they see a superconducting transition at 14 Kelvin. By now, a couple of other groups have synthesized very similar nickelates. There's about 5 groups throughout the world that can synthesize these nickelates successfully, even superconducting one, but it remains very difficult to synthesize a superconducting nickelate. So it's a complicated process. You first grow a film with a pair of skids, and you get rid of oxygen, and you can easily have some excess oxygen or excess hydrogen, as we have looked into here, in your system. And then the system just isn't superconducting anymore. Now, as for theory, we have actually to go 20 years back when Anisimov, Rice, and Baklavov predicted nickelates to be superconducting. They did DFT plus U calculations, and just from the apparent similarity to cuprates, they concluded nickelates should also be superconductors, or at least are very good candidates for that. This similarity includes the crystal structure, which is actually the same as that of the simples, but maybe not best cuprate superconductor calcium copper O2. So you have a nickel oxygen 2 plane, then you have this here a neodymium buffer layer before you have the other nickel oxygen 2 layer. So that very much reminds of the cuprates. It's even this very same crystal structure as one cuprate. And since nickel is neighboring copper in the periodic table, but if you take a trivalent instead of a divalent cation here, you end in a formal valency count in the same 3D9 electronic configuration. So that is very similar. We will see later also some differences, and that is kind of an ideal situation, because if you have two systems, nickelates and cuprates, that are similar and different at the same time, it's ideal to discriminate the essentials from the incidentials and to better understand high temperature superconductivity in both systems. Here's the outline of my talk. So whenever you have a new class of materials, you should start with the DFT calculation to get a basic idea of the relevant orbitals, and then you have to include correlations for such systems like nickelates and cuprates. So state of the art is, of course, DMFT to do so, and we have done so. Also, other groups have done so. So Andy Millis and Karp did similar calculation, and many others in the audience as well. From this conventional standard DFT plus DMFT calculation, we arrive at a picture that there's a very correlated x squared minus y squared orbital, but there are additional pockets. So that's different from the cuprates, but these pockets don't hybridize with the x squared minus y squared orbital. So in the first approximation, you can just consider them as a decoupled reservoir. That's the simplest model. There are more complicated ones, as I will point out later. But let's take the simplest model and see how far we come. We are then doing D gamma A calculation, dynamical vertex approximation. And we predicted the superconducting phase diagram at a time where only the very first experiment from the last slide was available. And in particular, with the most recent defect-free films, the agreement with experiment is just breathtaking and much better than we dared to hope. And also finite layer nickelates drawn by Giulia Mundi nicely agree with that picture. Now, of course, this agreement could be by chance, and so it's important to make further predictions and then to see whether it's experimentally confirmed or not. And there are two routes that we looked into more recently. One is to substitute nickelates by palladates. So our prediction is that these palladates should also be superconducting, and the best palladates even a little bit higher than present-day nickelates with a higher TC. We also looked into experiment under pressure. There's some experiment by Wang et al. From Beijing for this infinite layer compound, but only up to 12 gigapascal. And what we see here is really very interesting, because even without any chemical doping, our prediction is that the parent compound will become a superconductor at experimentally accessible pressures. But now let's look into the electronic structure, and let's start from density functional theory, comparing a cuprate and a nickelate here. So in DFT, you have this nickel x squared minus y squared orbital crossing the Fermi level. So you have a whole pocket, or in the Brion zone in pink, you have 4 of these Fermi surface sheets in the cuprates. Now, of course, that is a picture without correlations, and we know from the cuprates, if you now include correlations, this D band will split up into an upper and lower Hubbard band. And then the oxygen bands in light red here will actually be closer to the Fermi level. So according to Zahn and Sawatzky and Allen, then the cuprates are a charge transfer insulator, and you should use an Emery model or a Hubbard model at most to mimic the basic physics of the cuprates, but the more fundamental model would be an Emery model. Now, nickel is neighboring to copper in the periodic system. It's also +1. So in principle, this dx squared minus y squared orbital would just like to shift up. But because the Fermi level, if you have it at the same position for copper and cuprates and nickelates, still crosses this x squared minus y squared orbital. So if we fix the x squared minus y squared orbital via the Fermi level, everything else moves down. And that means that the oxygen bands are now far enough below the Fermi energies that the holes don't go in there. But what was the calcium orbital for the cuprates, now it's the lanthanum or neodymium 5d orbital, it's now crossing the Fermi energy at the gamma and at the A point. These are these 2 points here, and therefore you form these electron pockets. And because of the electron pockets, also the cuprates have a positive Hall coefficient, like for hole transport, whereas the nickelates, at least at low doping levels, have a negative Hall transport because of these additional pockets. Now, again, that is just a DFT picture. We now have to look into what correlations are doing. And to this end, we have done a fully fledged DFT plus DMFT calculations with 5 nickel and 5 neodymium d orbitals taken into account. And that is the result here. It's a relatively small window around the Fermi level. In white dots, you see the x squared minus y squared and the other orbitals of the DFT. And the false color is the DMFT spectral function. So you see here the renormalization by about a factor of 5. The spectral weight is also a little bit lower because, of course, you form Hubbard sidebands. Now, you see the x squared minus y squared orbital is strongly correlated. There's also the A pocket, which is very stable and always there. And then there's the gamma pocket. The A pocket, white line, and the false colors are essentially on top of each other, so it's no strong correlations. And also for the gamma pocket, it's more like a Hartree shift, what you have here, but no real strong correlation effects, what you see for lanthanum nickelate. Neodymium nickelate is a little bit different. There's a gamma pocket is still crossing the Fermi level, but if you dope the system, it also shifts up. And because, so here we clearly have a gamma pocket. For the other situations, and that's a superconducting doping, you likely don't have a gamma pocket anymore. And because the gamma pocket is varying so strongly for systems with very similar TCs, we think it is not so important for the physics of the nickelates, but there are other groups that have very different pictures. If we follow that, and from our DFT plus DMFT calculation, you can also see the z-squared orbital. It's here in the superconducting regime still below the Fermi energy. If you dope it more to 30%, it crosses the Fermi energy and you get multi-orbital physics. But in plain DFT plus DMFT, you don't get multi-orbital physics in the superconducting region of the phase diagram. And with that, our approach is that okay, let's make the most simple, most fundamental model for the nickelates and take Occam's razor to simplify it as far as possible, and then we just have one correlated orbital x squared minus y squared plus these A pockets. It even becomes a little bit better because the A pocket is made up out of this neodymium xy orbital. You have the nickel x squared minus y squared orbital in the other plane, and so you have a positive and a negative overlap, and they cancel, so there is no hybridization. So if an electron is in the pocket, it will never go to the x squared minus y squared orbital. And because of that, we can consider these two systems as largely decoupled. It's important, this electron pocket, to get the right hole doping. So if you make a chemical hole doping, part of the holes go to the pocket, the reservoir, and part go to the Hubbard model. But I've done many DFT plus DMFT calculations before, and that's actually the first time I dare to describe a real material with a Hubbard model, if we have this translation. And this translation of chemical doping to how much we dope this x squared minus y squared two-dimensional Hubbard model, that is what we can calculate in the full DFT plus DMFT calculation. It's a blue curve here. So even without strontium doping, you have something like 5% doping because of the electron pockets. And then about 50% of the holes go to the reservoir or the electron pocket, and 50% go to the Hubbard model. Please note that this is not a straight line. It has some curvature, and that will become important later on. We can then calculate for the single band Hubbard model all relevant parameters, the hopping parameters from a Wannier realization, and the Coulomb interaction from a CRPA. And then we can continue with D gamma A calculations, as I will show you in a minute. But before I do that, let me also point out that our scenarios, but also other groups like Andy and Karp and other groups have arrived at a similar minimal model. But okay, you know superconductivity, and there's a lot of fight of mechanism, and here's even a fight of what is the most fundamental or relevant model, and many different groups have arrived at different key ingredients that they think is important besides this minimal description. For example, at the beginning, there was a lot of excitement that you have a superconductor with 4f electrons. So some people thought that's important, but lantern nickelate has no 4f electrons, and so it doesn't seem to be so relevant. Then there is a z-squared orbital, which I mentioned before. So in other calculations, so for example, in SIG, DFT plus DMFT, it crosses the Fermi level, and then from that kind of calculation, you conclude it has to be included in the minimal model as well. And there are also further calculations. So this simple picture with just this x squared minus y squared orbital is, well, indirectly supported by Rick's experiments and their interpretation, which finds that actually most of the holes go to this x squared minus y squared orbital. Okay, But anyhow, there are very different scenarios in the literatures. That's the minimal scenario, and let's see how far we get with this kind of description. So the next thing we are doing is a dynamical vertex approximation, more precisely a ladder version of that with a lambda correction. What is it doing? So you all know random phase approximations. There you just have a geometric series, a ladder of bare Coulomb interactions. And if you do RPA, you can describe antiferromagnetic spin fluctuations and how they give rise to superconductivity. But it also very much overestimates antiferromagnetism and superconductivity. So in RPA, it's no problem at all to get a room temperature superconductor or even 1000 Kelvin. And what is wrong here in the RPA is there is no screening of this bare Coulomb interaction. It's just way too big. In D gamma A, instead of this bare Coulomb interaction, we take a local vertex, which is full frequency dependence, which we calculate from an impurity model. So it is similar to DMFT susceptibility calculations, except that you can do it self-consistently or in a Paquet approximation or with the lambda corrections, then you get corrections to these antiferromagnetic spin fluctuations of DMFT. And antiferromagnetism comes out much better. So there is actually a very nice paper of Thomas and Antoine, which compares various methods, including the D gamma A with also numerical methods like Monte Carlo simulations. And the agreement is really very good for the antiferromagnetic spin fluctuations. What we do here now is we go one step further. That is like a first step in a more fully Paquet approach. We take these antiferromagnetic spin fluctuations and go to the next channel, that is the particle-particle or Couperon channel where superconductivity lives. So this way we describe how antiferromagnetic spin fluctuations or magnons mediate superconductivity in our system. Maybe I should emphasize that we also describe charge fluctuations and other fluctuations on an equal footing. Just for the nickelates, the spin fluctuations are dominating, and we get D-wave superconductivity mediated by antiferromagnetic spin fluctuations. If you're interested in more details, there is this review of modern physics, but also this JFUS materials, which is very detailed. In a full Paquet approach, we would go back and iterate all of this, and then you get the full momentum dependence. So the main advantage not to do it self-consistently is that then we only get the main momentum dependence of the susceptibility or the vertex that is on the bosonic momentum. Now let's go to the results. So that is TC as a function of strontium doping. As I've explained before, you have to translate it into the actual hole doping of the x squared minus y squared orbital. And it's a non-linear scale, as you see here. That will become important. At the time of our calculations, there was this single experimental data point available, and that is the calculated TC. So we didn't adjust any parameters. We did the best we could do. If we would have used a larger U value, we would have been on top of experiment, but we thought that is a way too much, too large U parameter that shouldn't be realistic anymore. When later experiments came out, and that was the first experiment, and given that we really calculate TC without adjusting parameters, the agreement already here was very satisfying to us. But of course, there was a factor of 3 or whatever disagreement between experiment and theory. There was also this little dip in experiment. Many people jumped onto saying here you have D wave and then you have P wave, in particular for multi-orbital calculation. That was some outcome of their calculation. But it even gets better because the very same group as the previous data point shown here has more recent data, which are now defect-free. So there's an agreement both of the range of doping, of the amplitude of TC, and of the skewness of the curve is in very good agreement with the theoretical prediction. So in cuprates, we have a symmetric dome, but in the nickelates, it's skewed to the right-hand side because of this nonlinear doping dependence. Here, by the way, is the old experiments where you have a lot of stacking faults, and the new experiments don't have the stacking faults. It's a slightly different substrate, but that is less relevant here than getting rid of these stacking faults. You see that here the resistivity in experiment decreased by a factor of 3, and at the same time TC increased by a factor of 3 as well. The difference of the substrate could be maybe 3, 4, 5% in TC, but not such a big factor. Also, the 5-layer nickelate by Giulia Mundi nicely agree with the overall picture here. There, interesting to see is correlations in the 5-layer nickelates remove all pockets. And if you don't have pockets and you have 5 layers, you have a doping of 1/5 or 20%. So we are here, but since the 3 layers are slightly you have 5 layers and 3 inequivalent layers with slightly different doping. So we have this kind of uncertainty in the doping range where this 5-layer compound is. But it also agrees, and it now has a positive Hall coefficient, and all this picture makes sense. We can also compare the strength of the antiferromagnetic spin fluctuations. That is the theory for the very same calculations we did before. And that's the experiment. Here you compare the blue and the red maxima, and it nicely agrees, in particular if you consider that these were still the old films with the stacking faults and the smaller TCs and larger resistivities. So depending on what kind of disorder you have, if you have a more local disorder, you would expect that the antiferromagnetic coupling and therefore the width of the paramagnon dispersion is coming down. So the question is whether then the better films will also yield here a better agreement, or whether other disorder mechanisms are at play here. Okay, so all of that works very nicely, and okay, it could of course be by chance, so we should make new predictions, and in particular look into how we can increase TC, because that is one of the key issues for superconductors. And we started this by really just looking at the Hubbard model as a function of Coulomb interaction over hopping. That's the y-axis and the filling. And we have 3 different T prime parameters here. So that is a plain vanilla Hubbard model without T prime, and that is the relevant one for the nickelates. Also shown here is the superconducting eigenvalue. So if lambda equal 1, your susceptibility diverges, you get superconductivity. So at this temperature here of 60 Kelvin, everything yellow and red is superconducting, but everything green and blue will get superconducting also at lower temperatures. And what you see here is it's like a fingerprint, but it's very much deformed. That is this purple thing here. So what is the purple? And it's huge for the plain Hubbard model. It's where antiferromagnetic spin fluctuations get really strong. And if they get really strong, you form a pseudo gap, you lose your coherent quasi-particles, and that's bad for superconductivity. So that's why you get a superconducting dome in the first place, because you increase antiferromagnetic spin fluctuations going to half filling, but then they become too strong and TC goes down again. So very similar fingerprints have also been calculated in DCA by Emmanuel Gull and company. They couldn't go to so low temperatures, but it's a very similar kind of fingerprint as we get here, with slightly smaller lambda parameters or superconducting eigenvalues yet. Now, this sweet spot for superconductivity is that we actually have to decrease U, or we have to increase T, which is much easier in experiment. And at the very beginning, we proposed 3 different ways to do so. So pressure, or you can also make strain within your plane. And the strain will increase the overlap of the wave functions because the sides are closer together, and that will increase T. You can also use a different substrate, or you can go to wave functions that are more extended, like 4D palladates instead of nickelates with 3D. Now let's first start with the palladates. So our hope was to go with the palladates into this sweet spot region, and we also managed to do so. It turned out to be more complicated than we thought at the beginning. So if you just take lanthanum, palladium, O2, it goes down to 2 small U values. But if you have a more complicated palladates, like here in blue and orange, you hit the best region, and that increases the TC quite substantially. Then the other thing is pressure, and there is actually experiments, and this is now really the experiments for this infinite layer compounds. There are also recent experiments for 3 to 7 nickelates that are quite different. They have a different electronic configuration of D7.5, but these experiments are shown here. So applying pressure, you can increase TC in this infinite layer nickelates from 18 to about 30 Kelvin. And so in a most recent archive paper, we looked into the pressure. Again, we start doing a DMFT calculation without pressure and with pressure. That is now the praseodymium, because the experiment was praseodymium. And there are 2 effects with pressure. So one is what you expected. So this width here increases, as you can clearly see. And with the increase of the DFT widths, you also see that the DMFT band gets more weight. So the quasi-particle weight increases, and the dispersion also in DMFT gets larger. But there's a second point, that these pockets grow quite substantial under pressure. So without pressure, this gamma pocket is essentially 0, and with pressure, you get some larger pockets. So we have then done the same thing from the full DFT plus DMFT. We derived at all the first the lattice parameters under pressure and hopping. The Coulomb interaction in CRPA doesn't change very much, so we kept it as a constant. And these are the 2 things that are really relevant in changing under pressure. We looked into 4 different paths. So first is the plane phase diagram without pressure and comparing with experiment. Now this praseodymium nickelate, both in theory and in experiment, has a slightly smaller TC, but the agreement is again quite reasonable. When we have looked at in experiment, what they took is they took the maximal TC point, that's 18% doping. 18% doping, here's a red curve, and now they apply pressure. But the pressure they applied is just 12 gigapascal. So if we squeeze that into our figure, it's only going up to here. And if you see that here, it has a very similar slope. So about 1 Kelvin per gigapascal increase in TC. And that very much agrees with the existing experiment. It's not a prediction, but a confirmation. And we see here that TC will further increase before it dramatically decreases. So let's look at this 50 gigapascal, where we have the maximal TC. And that is the second phase diagram as a function of strontium doping. We again need a translation to doping. Now 0% strontium doping is 7% whole doping in this x squared minus y squared orbital. And that is enough, together with a larger T, to make the parent compound actually superconducting. So the electron pocket grows with pressure. The doping becomes so much that the parent compound at 50 gigapascal, according to our calculation, gets superconducting too. So let's look at the parent compound. And that's the last curve I'd like to show you here. That is 0% doping. So it's a yellow curve. So it first increases to this value, and then further increases up to almost 100 Kelvin. So it's as good as a cuprates before decreasing again. So how can we make sense of these calculations? Here is again this fingerprint I just showed you. It's replotted here, but now in a gray color bar. So dark regions are good for superconductivity. And we had these 4 paths here. 1, 2, 3, 4 paths. And 2 are at a constant pressure of 0 and 50 gigapascal. That corresponds to a certain hopping parameter and a certain U over T. So it's just going along here. And the other 2 figures were at constant doping, chemical doping, and changing pressure. But what is shown here is not the chemical doping, but the actual doping, which includes the electron pockets. And since the electron pockets grow, it's not a vertical line here, but you go in this curved way through your phase diagram. So without any pressure, 18% was the sweet spot for superconductivity. So it was experimentally the maximal TC. But if you dope it now, the electron pockets grow, you get more and more holes even, so you stick with 18% strontium doping, and you go to overdope. You go to the overdoped region. For the parent compound, instead, we were hugely underdoped without any pressure. But now applying pressure brings us to the 7% doping at 50 gigapascal, and then we cross the region where you have the maximal TC. And therefore, you get a maximal TC at around 50 to 100 gigapascal. Okay, with that, I'd like to conclude. So we have seen the minimal modeling that we looked into with just the reservoir and the Hubbard model. It's admittedly very basic and minimal, but it seems to be working pretty good for calculating the phase diagram. And with pressure, we see that you don't need doping or chemical doping. The system dopes itself if you apply pressure, and that I think is quite interesting also for experiment, because it's much easier to synthesize undoped nickelates. With that, I'd like to thank you for your attention and the following co-workers again, and here's a number of publications we have. Thank you very much.
Thank you, Karsten. We're open for questions now. Any questions from the chat? So again, people should raise their hands. Andy, you can.
Hi.
Hi, Andy.
Thank you for a beautiful talk. There it goes. Okay. First, a technical question. How did you include the A and gamma pockets in the D gamma A calculations for TCs? Or was this just done with the dx squared minus y squared orbital?
The D gamma A was just done with the x squared minus y squared orbital. All we did is to include the proper doping for them.
Okay.
So the idea of that is that the x squared minus y squared is the strongly correlated orbital, that it's certainly doing most of the spin fluctuations, and because of that, we presume also the superconductivity.
Right. Yeah. Understood. I guess that then there's a physics question which is beyond the scope of your talk, but I'll ask it anyway.
Yeah, sure.
So why is the A pocket so pinned? I mean, you can move the gamma pocket around by playing games with correlations and this and that, and you can't almost do anything with the A pocket. Do you know why that is?
Yes, so it's doing a reconstruction. So the A pocket actually goes much further down here if you look at the original A pocket.
Yeah.
but then it reconstructs with the other nickel orbitals. So it doesn't hybridize with the nickel x squared minus y squared, but it hybridizes with the nickel xy, for example. And therefore it ends here with the reconstruction instead of going further down. So if you shift it up, it will always end here at the bottom of the other nickel orbitals. It is not, so in a way, it is much deeper than it looks like because of the reconstruction. It ends here then, but it is therefore much less susceptible to move up.
I see. Thank you.
You're welcome.
Thank you very much. Antoine?
Karsten, thank you. That was a beautiful talk. I have a question about the palladates. So you have all these nice predictions. What do we know about their stability as compounds? Do we know anything about that? It's, of course, very difficult to predict, really.
Well, okay. The compounds we looked into are stable on the DFT level, so even on DMFT.
Yeah, sure. I'm sure they are.
Experimentally, it's not so clear, but experimental groups in Europe, China, Japan have started doing it, and there is some there is some interest. Yeah, there are also some companies even writing us because they want to use palladium or other expensive materials and sell it. And okay, yeah, so there is interest, but that's a challenge. And for the nickelates, it took 20 years to make them good enough to be superconducting. So it won't take 20 years to make them stable, I think. And I think DFT prediction in this respect are reasonably reliable, but to make clean palladates, I don't know. Maybe you need another trick like this calcium dihydrate reduction or so. That can be very challenging. So in this respect, nickelates under pressure, it's really something you can do. So you can just put your nickelate into a diamond anvil cell. The pressures of 100 gigapascal are no problem, but it can break. That is what we don't know.
Okay, thank you very much. Let's see. That's fascinating.
Okay, next is Irakli.
Hi, Karsten. Thanks for a beautiful talk. I have one question. When you show us the comparison between the experiment and your data, I have questions there. So as I see, the agreement is much better for high doping. Is some special, of course, the agreement is really very good in general, but especially it's good in high doping. In high doping, it's absolutely on top. So is any special reason for that?
Being on top is not what I predict the accuracy of the theoretical calculation to be. It's maybe also even nowadays with the cleaner films beyond the experimental accuracy. So it could be, I wouldn't be too surprised if it's even a little bit higher here at the end of the day than in the theoretical calculation, because they make even cleaner films in the future. I don't know. If it was a factor of 3, it's very impressive what they did, but you can't expect it to be on top of that. So we didn't adjust the parameter for that.
Okay, so my question was more, so there is no reason that the theoretical results agree experimental ones for higher doping
better,
or just it's a coincidence, let's say, that now they look like more close to each other.
Yeah, and I wouldn't exclude that it's just coincidence.
Okay, so thank you very much.
Thank you very much. Next one is Henri.
Yes, I am not very. Do you hear me?
Yes.
I am not very familiar with the nickelate, but I see the analogy with the cuprates. So I didn't understand whether you got the pseudo gap in your calculations?
Yes, so we get a pseudo gap for the undoped compound, also for the nickelates. Yeah, so maybe also here still, but in this, so essentially that the TC goes down here. That is a consequence of the pseudo gap opening.
Okay. So it's very similar then. The other question I have is I didn't catch the palladates are not experimentally done.
They are not grown yet. Yeah.
Which one do you find that you get superconductivity without doping?
That is the nickelates. So we calculated praseodymium nickelate, but the same story will be also true for lanthanum or neodymium nickelate. Yeah. So that is the easiest thing to do in experiment. You just have to put it in a pressure cell and
just high pressure.
High pressure.
High pressure. Okay, this is rather interesting and seems sound because I think that the way the doping is done in this system is rather original because you have a transfer from one band to the other in the plane. You don't need to have a reservoir outside. And that's the interesting point, which could be right experimentally because you do not drive any disorder.
Yes, so I think it's a very fascinating possibility to make it like that, just a self-doping with these electron pockets.
Yeah, okay, that seems rather sound. And in fact, you are getting, well, I don't know, there is...
Okay, so we are getting something close to 100K, but honestly, I would be happy if experiment gives you something like 60 Kelvin or something like that. Yeah, so there is some inaccuracy, of course, in the calculation.
No, but that's interesting because it also explains a little bit why in the cuprates, the 124, which is the same type of structure, is not getting to high TC.
Yeah. So one important difference to the cuprates is that all these nickelates, okay, let me continue here, that all these nickelates are grown from the bulk. The cuprates are grown also in the bulk, and the nickelates are all thin films. Yeah. So the variation of the square lattice parameters are much smaller in the nickelates. So most of the, so far at least, everything is grown on STO or very, very similar substrates. And then in cuprates, you have a much larger variation of the hopping parameters because you have bulk systems. And then if you have different numbers of films, you change the system, the in-plane hopping also quite substantially.
Okay, I liked your talk. So sorry, I didn't say it, but nice talk.
Thank you.
Okay, before the next raise, then there's a question in the chat. So Angui Chen, you can ask your question.
Sure. Can you hear me?
Yes.
Okay. Yes, Professor Held, it's a very beautiful talk. Can you just show the Fermi surface of Palladian nickelate and high pressure?
Okay, so it is now, I had again a technical problem right now. You didn't notice it maybe, but I can't actually. Yeah, not so.
Okay. Oh, okay. Okay, so that's very unfortunate.
I can send you an email for sure. So what did you want to see with the Fermi surface?
What I want to see, okay, so if I remember correctly, on the 50 gig part, the Fermi surface of Palladian nickelate has two sheets, right?
Yes, it has a pocket and it has this whole one which of the x squared minus y squared orbital. So
okay, so my question is that for Palladian nickelate on the 50 gig part, can we still use the single orbital hub model plus a reservoir to describe it, or we need a two orbital model?
That is a good question. So it's still the situation that these pockets are not very strongly correlated, but they grow. And at one point they grow and it becomes maybe a little bit more questionable, but not so questionable that we wouldn't think that the TC will increase and that you will get enough hole doping to make it superconducting. So if you go to 200 gigapascals, then this pocket will even touch the x squared minus y squared orbital. And in this situation, for sure, latest, the single orbital description breaks down.
Okay, but when you show this TC, so when you calculate all this TC, you still use the single orbital model.
It is still in the single orbital model, and even though the pocket is larger, and it's the gamma pocket, we did the single orbital calculation. But this actually, it's a result of the fully 5 + 5 DFT plus DMFT calculation. So you should have this much of doping into your x squared minus y squared orbital, and there's no, in DFT plus DMFT, there's no z squared orbital yet either. So, and these pockets remain weakly correlated. So the basic setup is the same, but of course, you can ask yourself up to which size of the pockets do you think it's possible to do it in a single orbital calculation. And there I would say up 100 gigabytes are likely, but maybe not at 200 or 150 anymore. But
okay, we're gonna go for the next question. So Kanker.
Hi, Karsten. It's good to see you again.
Nice seeing you again.
Yeah. So I had a question which is probably a bit on the technical side also. It has to do with this parquet-like thing that you're showing for calculating the spin fluctuation and then going to the particle-particle channel. So if I understood it, it's not done self-consistently, right? So you calculate the particle whole response and put it into the particle-particle channel, but you don't cycle it back, right?
That is right.
So any thoughts on what could change if one could actually, I understand it'd be a difficult calculation, what you might expect?
So we have done such full parquet calculations, but only at much higher temperatures. So their lambda is nowhere close to 1 yet, because it's much more challenging numerically.
Yeah, I understand that. So,
a naive expectation of mine is that it somewhat reduces the TC, because typically, in my experience, I don't know, if you get something too strong, then it feeds back and it suppresses it somewhat, but that is only some gut feeling. It's not really based on actual results.
Okay, thanks.